Hey guys, welcome to the second video about molecular geometry. We're going to look at some slightly larger molecules today. The Vesper model is still going to be the model that guides our thinking. So we're always going to try to minimize repulsion among electron pairs. So let's start with writing a Lewis electron dot diagram for PF5. Again, if you're seeing this lesson for the first time, why don't you pause the video and try the Lewis electron dot diagram. It's good practice. And once you've done that, hopefully this is the diagram that you came up with. This is an example of an expanded octet. So the 5 fluorines are attached to the central atom, and remember that the central atom can have an expanded octet as long as it's not carbon, oxygen, nitrogen, or fluorine. Okay, now we have got to arrange 5 electron pairs in such a way that they are as far apart from each other as they can be. This is a really different kind of structure. This is what it looks like. So first of all, I want you to notice that there is an axis, an up and down vertical piece. These bond angles are 180 degrees apart, and then they're 90 degrees from what I refer to as the equator. So if you look at the molecule this way, you can see that there are 3 bond angles 120 degrees apart on the equatorial plane. This arrangement is called Trigonal Bipyramidal. So think of the equator plane as a triangle. That's the base of a pyramid that stretches above the equator, and a second pyramid that stretches below the equator. Trigonal bipyramidal. And if your molecule has 5 electron domains around the central atom, and all 5 of those domains are bonds with no lone pairs, then the molecular geometry has that same name, trigonal bipyramidal. Okay, the next one I'd like you to draw is sulfur tetrafluoride, SF4. F4. So take a moment, please. Draw the electron dot diagram. And this is the structure that we get. And we find again that the central atom has an expanded octet. There are 5 electron domains around that central atom. 4 of them are bonding pairs, and 1 is a non-bonding pair. So we're going to take our trigonal bipyramidal structure with those 3 bond angles of 120 on the equatorial plane, and then the axis that's 180 degrees. And one of the electron pairs on the equator plane, sorry, that's my dog. One of these electron domains is not a bonding pair, but a non-bonding pair. Now that is going to result in a little bit of distortion. Sorry, Gracie. My husband's mowing the lawn. That's going to result in a little bit of distortion, both on the equator and also on the axis. I'm exaggerating it here. So when that is the case, the molecular geometry has the very scientific name of seesaw. I don't know if you can see any seesaw action here. Think of it as kind of dipping back and forth, seesaw, with a little alien sitting on the seesaw. Okay, so 5 electron domains around the central atom. 4 of them are bonds, and 1 is a lone pair. Okay, the next one is chlorine trifluoride. So draw its electron dot diagram. And we have yet another example of an expanded octet on the central atom. Remember, guys, you can never put your leftover extra electron pairs on a peripheral atom. Always on the central. So here again, we have our 5 electron domains that have to try to get as far apart from each other as they can. Whenever your number of electron domains is 5, you'll have 3 on the equator and then 2 in the axial position, and 2 of the equatorial electron domains will be non-bonding pairs, and the 2 non-bonding pairs are going to repel a lot, which is going to cause a little bit of distortion of these guys. Now, see if you can think of what the name of the molecular geometry would be. Remember, on molecular geometry, you're just letting your eye follow the atoms and the bond angles in the atoms. We're ignoring the lone pairs to name molecular geometry. So this permutation of 5 electron domains is called T-shaped. We have 3 bonds and 2 lone pairs. Can you see where the name T-shape comes from? Okay, next, please draw the Lewis electron dot diagram for xenon difluoride. This is what you should get. And again, our central atom has an expanded octet. Notice that it has 1, 2, 3, 4, 5 electron domains. So again, we have 5 toothpicks around your central marshmallow. And this time, the 3 non-bonding pairs will all be on the equator. And I'm gonna fix this guy. The 2 axial positions are still intact. See how the bond angle is now 180 degrees? That's good separation. And in naming the molecular geometry, we're ignoring the lone pairs. We're just looking at the atoms that make up the molecule, and hopefully you can see that that geometry is linear. Okay, almost done. Draw, please, the electron dot diagram for sulfur hexafluoride, SF6. Okay, here's what we get. Definitely an expanded octet. The central atom has not 4 bonds, but 6 bonds. Expanded octet. Now, if you are following Vesper theory and you have 6 electron domains around the central atom, we have to figure out the best way to minimize repulsion by creating maximum bond angles. And when you have 6 electron domains, the best separation you can get looks like this. On the equatorial plane, we're going to have 4 electron domains, all at 90 degrees separation. And then we're also going to have an axis with 180 degrees and 90 degrees from each to the equator. Okay, so 6 toothpicks, 6 electron domains, 4 evenly spaced on the equator, and then 2 along the axis. This geometry is called octahedral. And if you have 6 electron domains and they are all bonds with no lone pairs, the molecular geometry is also called octahedral. Then I'd like you to do bromine pentafluoride. Oh Lord, so much background noise today, sorry. BRF5. Pause the video, draw the Lewis structure. Here's what you get. Central atom has 1, 2, 3, 4, 5 bonds and a lone pair. That's, again, 6 electron domains. So we're going to put our 6 toothpicks in this octahedral configuration, 4 on the equator and then the axis, and one of the bonds, one of the electron domains is not a bond but a lone pair. The name of this geometry is square pyramidal. You have a square here on the equator. Gracie girl. Shh. Okay. We have a square on the equator, and then we have the tip top of the pyramid. This is a pyramid with a square base. So 6 electron domains, in which 5 are bonds and 1 is a lone pair, has the name square pyramidal. All right, guys, and the last one. Draw, please, the electron diagram for Xenon tetrafluoride. This is your electron dot diagram. Xenon, our central atom, again has 6 electron domains. This time there are 1, 2, 3, 4 bonding pairs and 2 non-bonding pairs. But 6 electron domains, again, means we have to maximize bond angles with an octahedral configuration. The 2 lone pairs are going to be opposite each other. So that gives the best separation between these big old non-bonding pairs. And then the bonds will all be arranged at 90 degrees from each other on the equatorial plane. The name of this geometry is square planar. It's flat as a pancake. Remember, as you're naming the molecular geometry, you're ignoring the lone pairs, and you're just looking at the atoms and the bonds that connect them. Square planar for this one. Okay, guys, so in summary, you have this table in your textbook, and it just puts together everything we've just talked about. When you have 5 electron domains around the central atom, your bond angles are 120 around the equator, and then you have an axis that's 180 degrees with 90 degrees to the equator. If all 5 of the EDs are bonds and no lone pairs, the molecular geometry is trigonal bipyramidal. If 4 of the EDs are bonds with 1 lone pair, that's called seesaw. If you have 3 bonds and 2 lone pairs, your molecular geometry is T-shaped. And if you have 2 bonds and 3 lone pairs, the molecule is linear. When we have 6 electron domains, the geometry is octahedral with just 90 degrees in every direction. If all 6 EDs are bonds, the molecule has geometry, octahedral. But if you have 5 bonds and 1 lone pair, your geometry is square, pyramidal. And if you have 4 bonds with 2 lone pairs, you have a molecule whose geometry is a square that is planar, flat as a pancake. All right, guys, hope that was helpful. Thanks.